Hi guys, so some of you are having some trouble with section 6.2, so I wanted to make a short video here to try to clean things up and go over some more examples to hopefully get you on track. So what I have up here are just some lecture slides from 6.1 just to remind you of. So if you remember, this was a slide in 6.1, and when we're dealing with a continuous variable, it's not going to look exactly like discrete, right? So remember, what we have is what's called a probability density curve, so something like this. So we can't we can't necessarily have like a table showing a probability function for something that's continuous because we can't possibly list all the points, right? So if we look back here on the next slide, I have here a scenario where a bus is arriving at a certain stop every 12 minutes. It just so happens that this is going to be a uniform distribution. So the reason why that's important, uniform, right, means it's flat, right? It's flat the whole time. So the reason why, if you remember back from 6.1, the reason why this was useful was because we can calculate area of a square pretty easily, right? So the next slide, right, if I want to find the area or the probability of waiting between 4 and 10 minutes, right? Essentially, I want to find the area between 4 and 10. So we talked about how between 4 and 10, this is a length here of 6, right? And then going this way, the top is 0.08333 repeating, right? So you can see that's why we have this calculation here, right? Taking the length times the height. Getting about a probability of 0.5, right? So then this last slide, I was just talking about how, typically when we're trying to find areas under a curve, it's not so easy to do if it's not a rectangle. So we want to use some type of technology to do so, right? So what I have pulled up here now is this worksheet that I posted on Canvas. So it's section 6.2 practice problems. So I picked, I think, four problems here. I want to work through them with you, and I'm gonna just remind us how to do this calculation on the calculator, right? So the two functions that we're going to be using in the calculator are the normal CDF and the inverse norm, right? And don't forget, we already talked about these two, right? So if we use the normal CDF, this is to find area, right? Or in other words, probability, right? The area is the probability. And this guy is to find the x value, right? Given the area, right? So if you look at the section 6.2 PowerPoint slides, right? I can pull these up really quick. Let me download them. Right, so in the 6.2 lecture slides, we actually went through scenarios of should we use normal or inverse normal, right? So towards the end, a couple of slides, right? So don't forget how to identify those, right? All right, so let's work through some problems. So number one, there's two parts. So it says a line up for tickets to a local concert had an average mean waiting time of 20 minutes with a standard deviation of 4 minutes, right? And we want to make sure we pay attention to the directions here. It does say construct a normal distribution curve each time, right? And also make sure you label the horizontal axis, right? So when you're working through these kind of problems, I'm expecting you to make the curve and draw the axis every time. And this is also stated in concept check number 6, right? So I want to make sure I show you how to do that. So as I'm reading this, I find that we have a mean of 20 and a standard deviation of 4, right? So if we just draw a curve, right, a normal curve, right, unimodal symmetrical curve, a bell curve, what I'm trying to find is what's the probability that someone waited more than 28 minutes, right? So in other words, I want to know what's the probability that x is greater than or equal to 28, right? And actually in this section, the the greater than or equal to sign doesn't make a difference, right? So when we do a continuous probability, that doesn't make a difference. But you're going to see in section 6.3 a type of a discrete probability is called a binomial probability, and that is going to make a difference, right? But for this section, it doesn't make a difference. So you could also put x greater than 28, right? And the area will actually be the same, right? So it makes no difference. So basically what we want is somewhere in the center here, right, is going to be my mean of 20. And I'm trying to find greater than 28, right? So here's 28. So basically what I'm after is this area. I want to know the area of the curve for x greater than 28, right? I want to know what this area is. This area is going to be equal to the probability, right? So we could use integral calculus to find this, but since this is an algebra-based stats course, we're just going to use our graphing calculator to do so, right? So let me turn my calculator on. I'll just go to second distribution, and then we're going to use the normal CDF, right, which is there. So we want to go from 28 to infinity, right? So don't forget, that's how we code. Infinity is 1e99, and how you get the e is you hit second and then this button here, right, the comma. So then my mean is 20, standard deviation is 4, right? And there's a probability, right? So the probability of waiting more than 28 minutes is about 2.3%, right? So 0.023 roughly, right? So it didn't specify a set number of decimal points around, right? So maybe we'll do just about three decimal points, right? So then now number B, it says if 2,000 ticket buyers were in line, how many of them would expect to wait for less than 16 minutes, right? So my idea of thinking is let's make a curve, right? So my mean again is going to be somewhere here in the center, right? Here's my mean of 20. And we want to find less than 16, right? So somewhere over here is going to be 16, right? So left of 20. And I want to find less than 16, so I'm looking for this area. This area is the probability that x is less than 16, right? So my line of thinking is let's find that, because that's going to give us a percentage of people we would expect to be less than 16, and then I can just multiply that number by 2,000 to find the total number of buyers, right? So let's find this probability of, oops, let me erase that. So probability that x is less than 16, right? Let's find that, and then to find the number of ticket buyers. That weight less than 16. So the number of ticket buyers that we expect to wait less than 16 minutes would be equal to the probability of x less than 16 times 2,000, right, is what I was saying. Right? So again, we can just use our calculator. So I go second distribution. I want to find the area again, so I'm going to use normal CDF, right? Remember the C1 means continuous, right? Continuous density function. So I want to put in my lower is actually going to be negative infinity, right? So we do negative 1 E99, and then my upper part, right, is going to be 16. And then my mean is 20, standard deviation is 4 still, right? So if I hit enter again, that's the probability. So we get 0.15865, right, and some more decimals. So now if I just come over to my calculator and hit times 2,000, we get that we would expect about 317, right? So we would expect about 317 people to wait in line less than 16 minutes, right? So hopefully that makes sense, right? Because this area is a percentage, right? These are so in other words, kind of the probability. The way of thinking about it is if I have 100 people in my line, then going from negative infinity all the way to 16 is going to give me this percentage, right? So then I don't have 100 people in line, then I have 2,000, right? So that's why we had to multiply that percentage times 2,000, right? So then if I go down number 2, it says on a recent math test, the mean score was 75 and standard deviation was 5. Mike made a 93, right? So I would come in, I don't know, let's change my color to blue, right? So let me just identify the mean is 75. The standard deviation, whoops. There. So then the standard deviation is 5, right? And I should have used mu here, right? So we have mu of 75 and sigma, which is 5, right? So the question is, what is the 25th percentile, right? So if you remember back to 25th percentile, if we have a normal curve, there's going to be some line in the sand, right, where the area to the left of this number that we don't know, we'll call x, we want 25% to be to the left, right? So this would have to use the inverse norm, right? Because we know what the area is to the left. We want it to be 25%, but we don't know what this x is. That's what we want to find. So it's the opposite of what's up here, right? So up here, we were given like some x value, and we use the inverse norm function to find this area to the left, right? So to be able to find that x value, I'm just going to use inverse norm, right? So if I come over here to my calculator, go to second distribution, and then the third option, inverse norm, and then so the area I'd put in is 0.25, right? And this area, it's always going to be to the left, right? So if you have a more recent calculator, you might have an option to put in like left, right, or center, or whatnot. But if you don't have those options, it just always does the left by default, right? So we would do 0.25. My standard deviation, or my mean is 75. My standard deviation is 5. And if I hit paste, now I found this line in the sand, right? So x should be 71.627, right? Roughly 726, right? So another nice feature that we can do in our calculator is I can actually store numbers. So rather than like writing down all these numbers, what I can do is I can just come down here and hit this STO button, so store. And then if I go to second, or excuse me, not second, I want alpha. So I pick a letter. So I can go alpha like A. And then so anytime I reference A, it's going to use that number. It stores that number instead, right? So I stored this as A, right? So we can just make note of that, that I stored this Q1 as A, right? Because 25th percentile is same as Q1, right? So then part B, we want to find Q3. So similar idea, right? I have this normal curve. There's some x value here that I want to know. The area to the left is 0.75, right? 75%. So, and this is the same thing as Q3, right? So then if I go second distribution, do inverse norm again, right? Same rationale. The only difference is the area needs to be 0.75. So then I get that value, right? So the x value is about 78.372, right? But again, I'm going to store this as B, right? So I'm going to hit store, alpha B, and now my answer is stored as B, right? So this was stored as B in my calculator. And really these A and B thing isn't something you necessarily write down for me. This is more for you, right, to remember what variable you use when you stored, right? And you don't have to write, if you don't have to do store, but I knew in number C I was going to use the values from A and B to generate C. So it's bad to use a rounded answer to get another answer. That's what we call rounding error. in math, so you can be off a little bit, right? But for part C, it says using the values you found in parts A and B, determine if Mike's score is an outlier, right? So Mike's score was 93, right? So if I just think about this a little bit, I have this normal distribution. So somewhere in the center here is the mean, which is 75, and Mike's score is over here, 93, right? So I want to know, is this an outlier, right? So if you remember, this would be to the right, be to the right of the mean, right? So really what I'm looking for is what's the upper limit, right? What is the upper limit? Right, so you would have done this, when you made box plots, right, to determine if something is an outlier or not. So what I would want to do is take, define the upper limit, right? Remember, I would take quartile 3, and then plus 1.5 times the IQR, right? But the IQR, if you remember, is Q3 minus Q1, right? How to find that? So in other words, if you remember, I stored this as B, I stored this as A, right? So the IQR would be B minus A in my calculator, right? So if I come up here and do, excuse me, if I do alpha B and then minus alpha A, there's my IQR, right? So this was about 6.7449, right, rounded, right? So I'm going to store this as the variable C, right? So then I go to store alpha C. So now I have that answer stored as C. So now when I come in and want to find the upper limit, right, the upper limit would be equal to Q3, which I stored as a variable B, right? So in my calculator, I'd put in B, and then plus 1.5 times C, right? That would be how I put it in my calculator using the variables I stored. So if I come up here and go alpha B plus 1.5 times C, I get the upper limit of 88.49 roughly, right? So this 88.49 is going to be here, right? So remember the upper limit, right? This is my upper limit. Then anything to the right is an outlier, right? So the score of 93 would be an outlier then, right? So since 93 is greater than my upper limit, it is an outlier, right? So we would say, yes, it's an outlier, right? So Mike's score is an outlier, right? So that's how we would determine that, right? All right, so we have 2 problems left, right? So if we're looking at number 3, it says in an Oreo factory, the mean mass of a cookie is given as 40 grams. For quality control, the standard deviation is 2 grams, right? So again, I just want to make note of the mean standard deviation. So the mean was 40, and the standard deviation was 2, right? So it says A, if 10,000 cookies were produced, how many cookies are within 2 grams of the mean, right? So within 2 grams. So my standard deviation is 2 grams. So this is finding, how many cookies are within the within 1 standard deviation, right? So if I come over here, draw my curve, right? Again, somewhere in the center is going to be 40 grams. And then if I go 2 grams this way and 2 grams this way, right? That's what this within 2 grams means. I would be in between 42 and 38, right? So let me try to draw this up here a little higher, right? So 38 and 42, right? So and again, over here was the mean, right? So I went 2 this way and 2 this way. So then what I'm after is, well, let's find the probability or the proportion of cookies that are inside of this range, and then if I multiply that by 10,000, it'll tell me the number of cookies then, right? So I'm going to want to use the normal CDF in my calculator, right? So my lower would be 38. My upper is 42, right? My mean was 40. Standard deviation is 2. Right, so this gives me that area, right? So the area here, right, or in other words, the probability of being in between 38 and 42 is equal to about 68%, right? And we also already knew that from the empirical rule, right? So if you remember back, I actually reminded you this in section 6.2, I think. Let me double check here. So I put the empirical rule here to remind you that if you're within 1 standard deviation of the mean, we expect about 68%. Within 2 standard deviations, about 95%, and then within 3 standard deviations, about 99.7%, right? And this changes, right? Because if you remember from my 6.2 lecture video, the shape of the normal distribution actually changes depending on the standard deviation and the mean, right? So if you remember, we looked up here, right, on this slide. So slide 4 showed you, how does the standard deviation change my shape, right? So if I keep the mean the same and change my standard deviation, it changes like how spread out the data are, right? So it changes like, is it really narrow or really more flat, right? So that's certainly going to change the area, right? Between -4 and 0 for the blue and red curve would be totally different, right? And then number 5, right? So basically changing the mean but keeping the standard deviation the same. The shape remains the same, but it's kind of moved over, right? So it kind of shifts the curve left and right, right? But so all of those things are going to contribute to changing how the area looks, right? So that's why we have to specify in our calculator what's the mean, what's the standard deviation every time, right? That's one of the inputs that we need, right? So then to answer this, I need to take this 68% value, multiply it by 10,000, right? Because I have 10,000 cookies. So if I just come over here and hit times 10,000, right? So 1, 2, 3. I got too many zeros. Let me get rid of 1. Right? Should be right. So if I hit enter, we're getting 6,827 roughly, right? Cookies, right, are going to be within 2 grams of the mean, right? So let me get rid of this here. Right. So now if we look down at number B, it says cookies are rejected if they weigh more than 44 grams or less than 36 grams. How many cookies would you expect to be rejected in a sample of 10,000 cookies, right? So so basically here's our normal distribution picture, right? Remember the mean is somewhere here in the center at 40, but what we're looking for is between 36 and 44, right? Hang on, it's kind of a bad 4. All right, I don't know why that's connecting. So that's 44, right? So what we're after is if we find this area, this would be the area of the cookies that are good, right? That are safe to eat, or in other words, not rejected, right? They're within the weight that we want, right? But then if we look at this area here and this area here, these are rejected, right? So an easy way to find this, how I would approach this is if I take 1 minus the good area, that's going to be equal to the rejected area. Right, because remember the total area under a curve is always 1, right? So that's one way to do this, right? Another way, since we know this is normally distributed, is you could find one of these areas and then double it, because these areas are going to be the same, right? So this is called a tail, and this is called a tail, right? So if I look at my left tail, and this guy we'll call the right tail, these areas are going to match, right? So what I could do is also to find the total rejected is I could take 2 times the left tail, right? Or I could do 2 times the right tail, right? And that would also give me that area, right? So what I would do is go to second distribution. I'm going to do normal CDF. So the way I'm going to approach this is I'm going to use this the top one minus the good, right? So first off, let's find the area between 36 and 44. So we come over here and we do 36, 44. My mean standard deviation is still the same, right? So that's 0.95, right? So this area here is 0.95 roughly, right? So then if I go 1 minus that answer, I get the area of the red, right? So the red area is this number, 0.045, right? So then if I have 10,000 cookies, I multiply this by 10,000, I get 455. So that would be my final answer, right? 455 cookies would be rejected, right? Rejected, right? And rest assured, I'm sure they wouldn't actually get thrown away, right? They'd probably get thrown in, to make like Oreo cookie crumbles for baking and so forth, right? So there's certainly other uses, right, that we can do. They just don't fit within the range that the company wants to have, right? They want to have a specific weight. All of them be a similar weight, right? All right, so lastly, number 4 is talking about speed. So let's see. So let's write down the main points here. So I have a mean of 95. Right, I have a standard deviation of 5 kilometers per hour. So we want to say what percentage of cars average less than 85 kilometers per hour, right? So we want to know what's the probability that x is less than 85, right? So here's my picture, my curve. My mean is somewhere here, 95. But I actually want to find the area 85 to the left, right? Less than 85. So this probability is that shaded region, right? So then if I just come over here, so second distribution, normal CDF, we would go negative infinity to 85. And then my mean is 95, standard deviation of 5. I get this amount, right? So then if I multiply this times 100, that will put it as a percentage, right? Because that's what we're asked. What's the percentage? So we would say 2.275%, right? So 2.275% of the cars we would expect to be traveling less than 85 kilometers per hour, right? So then this last one says if a police car stopped cars that were going more than 105 kilometers per hour, how many cars would we expect to stop if we had 8,000 cars on the highway, right? So again, let's figure out, well, what's the percentage of cars we would expect to be going more than 105 kilometers per hour? So right here's 105. I want to find the area to the left. Right, so if I go to second distribution, normal CDF, we want to go 105 to positive infinity. Whoops, didn't get the 1 in there. Second, insert 1. Right, and then the mean deviation is the same, so I can just go down, hit paste. So that's the area and also the percentage, right? So I would expect 2.275% to be bigger than 105 kilometers per hour. So then if I multiply that times 8,000 cars, right, I get 182, right? So out of the 8,000 cars, I would expect about 182 cars that are being stopped for going over than 105 kilometers per hour, right? All right, so hopefully this helps you understand the homework better, understand the shading, and also concept check 6, right? So if you have questions, please post on the discussion board, send me an email, I'll be glad to help. Thanks.